Assalamualaikum, students and friends. Welcome back to Sir K's playlist of physics tutorials. Today's episode is a sequel of past upload titled Complete Static Equilibrium. We analyze the forces acting on a uniform rod and explain why the rod stays in complete static equilibrium. So just stick around, watch and learn. The question is, a 3.00 meter long, 190 Newton uniform rod at the zoo is held in a horizontal position by two ropes at its ends. See the following figure. The left rope makes an angle of 150 degrees with the rod, and the right rope makes an angle theta with the horizontal. A 90 Newton Howler monkey, scientific name Eleotta seniculus, hangs motionless 0.50 meters from the right end of the rod as he carefully studies you. Calculate the tensions in the two ropes and the angle theta. First, make a free body diagram of the rod. The body in question is a uniform and rigid rod 3.00 meters long, held in a horizontal position by two ropes at its ends. The left rope makes an angle 150 degrees with the rod, and the right rope makes an angle theta with the horizontal. All right? A 90 Newton Howler monkey hangs motionless 0.50 meters from the right end of the rod. Since the rod is of uniform density, its weight of 190 newtons passes through its center of mass, while the weight of the Howler monkey, which is equal to 90 newtons, has a line of action 0.50 meters from the right end of the rod. And our target variables include the tension force T1, which is exerted by the left rope, all right, and is directed as shown. The second target variable is T2, or the tension force exerted by the right rope. And of course, our third target variable is the angle theta. And we are assuming that these forces, all right, acting on the rod, such as T1, T2, W1, and W2, we consider them as coplanar forces. In other words, the four forces all lie in one Cartesian plane. And as shown in this vector diagram, these four forces are non-concurrent, meaning their lines of action actually do not pass or they do not intersect at a common point. All right. Earlier, we said that the tension force T1 makes an angle of 150 degrees, okay, from the horizontal, and that means the angle that it makes with the negative x-axis is equal to 30 degrees. And so therefore, we can express the x and the y components of both tensions T1 and T2. All right, for t sub 1x, this is the x component of T1, we can say that t sub 1x is just equal to t sub 1 times the cosine of 30 degrees. And its y component is equal to T1 times the sine of 30 degrees. Or simplifying, all right, t sub 1x is just equal to 0.867 times T1, while t sub 1y is equal to 0.500 times T1. Likewise, for T2, all right, where T2 is described, the direction of T2 is described as the angle theta, all right, which we still have to determine later. But we can already express the x component of T2, all right, in terms of the cosine of the angle theta. That is, t sub 2x equals t sub 2 times cosine theta, while the y component, t sub 2y, is equal to t2 times sine of the angle theta. All right? And since we consider the rod to be in static equilibrium, that means the summation of all forces along the horizontal, that is denoted here by this symbol, summation of fx, we say that summation of fx must be equal to 0, right? So that means t sub 2 cosine theta, okay, when added vectorially with t sub 1x, all right, we come up with this equation. So summation of fx, which is 0, is equal to t sub 2 cosine of the angle theta minus 0.867 times T1. All right? Or simplifying, we will have this equation number 1, which relates T2 and T1. That is, T2 multiplied by cosine of the angle theta is just equal to 0.867 times T1. When we say that the rod is in static equilibrium, that also includes the fact that the summation of all vertical forces, denoted here by summation of Fy, must also be equal to 0. All right? So earlier, we already stated, okay, the fact that the summation of Fx must be equal to 0. And these two conditions for static equilibrium, together with the third condition, all right, which states that the summation of the torques produced by all the forces acting on the rod must also be equal to 0. So, when we are able to satisfy all these conditions, all right, we say that the rod must be in complete static equilibrium, which simply means that the rod is not going to have any translational motion or rotational motion. All right? So, uh, since our task is to determine the target variable, which is t sub 1 and t sub 2, all right? And we were able to start using the condition that the summation of fx must be equal to 0. So we shall now continue, this time, using the fact that the summation of fy must be equal to 0. All right? As shown in the diagram, all right, the upward forces, which are t sub 1y and t sub 2y, okay, when added, must be equal to the downward forces, such as the weight number 1 equal to 190 newtons, that's the weight of the rod, and the weight of the monkey, which is 90 newtons. All right? So as given here in this equation, the vertical forces when added, okay, vectorially, their sum must be equal to 0. All right? So t sub 1y is expressed as 0.500t1, while t sub 2y is the same as t sub 2 sine theta. All right? And the downward forces are negative 190 newtons because it is directed downwards, as well as negative 90 newtons, which is also directed downward. So all these four forces, when added vectorially, their sum must be equal to 0. All right? So when we simplify, all right, we get this equation number 2, where the downward forces have been added, and that's equal to 280 newtons. All right? And the upward forces, T1y and T2y, are expressed as 0.500T1 plus T sub 2 sine theta. And earlier, we already have come up with equation number 1. So we just want to emphasize once again, equation 1 relates the two tension forces, T sub 2 and T sub 1. That is, T sub 2 cosine theta is just equal to 0.867 T sub 1. All right? So in the next steps of our computation, we will be using these two equations. We will now apply the principle of torque, all right, which states that the net torque, or the total torque produced by all the forces acting on the rod, must be equal to 0, which simply means that we are assuming the rod is not going to rotate. All right? So what is the torque principle? We can say that uh, the torque that causes the body to rotate in clockwise direction, all right, we write it like this, CWT, which means the torque that's causing the body to rotate clockwise. And among the forces here, all right, among the forces acting on the rod, okay, we will only consider three: T sub 1y, W1, and W2. All right. So I don't want T sub 2y to be included in my equation. So I'm going to use point B as my axis of rotation. All right. The choice of the axis of rotation is actually arbitrary. That's just a matter of convenience. I choose point B, all right, as the axis of rotation, so that I don't have to include uh, the force T sub 2y in my equation, all right, because any force that is uh, or whose line of action passes through the axis of rotation will have no corresponding torque. Okay, the torque produced by T sub 2y about point B must be equal to 0, right? And it will make my computations easier, all right? The problem with T sub 2y, all right, which is actually the vertical component of T sub 2, okay? We don't know yet the magnitude of T sub 2, and we don't know the angle theta that it makes with horizontal. So we will be dealing with two variables, and that will pose a problem, all right? So that would mean now I will only consider the forces T sub 1y, the 190 newtons, and the 90 newton forces. So in my first equation, I have here the torque that produces or that will make the rod rotate clockwise, and that is due to the effect of T sub 1y. Okay? If you look at the direction of T sub 1y relative to the axis of rotation, which is point B, all right? T sub 1y is going to have what we call a clockwise effect on the rod. It is as if it's going to make the rod rotate in a clockwise manner. All right? So, how do we express the torque due to T sub 1y? It is simply the product of the magnitude of the force T sub 1y already expressed as 0.50 T sub 1, and then multiply it by 3.00 meter. What is 3.00 meter? That is the corresponding lever arm of T sub 1y. By definition, the lever arm is the perpendicular distance from the line of action of the force, all right, to the chosen axis of rotation. And here, the lever arm that we use is simply equal to the length of the rod, equal to 3.00 meters. So, multiplying them, all right, in terms of T1, we have this, what we call the torque, okay, due to T sub 1y, which is 1.50 meters times T sub 1, right? And similarly, the two other forces, 190 newtons and 90 newtons, all right? Each of them will also have a corresponding torque, okay, relative to the axis of rotation. Okay, you can figure out that 190 newton will somehow cause a counterclockwise torque. All right. In other words, it's going to make the rod rotate in counterclockwise direction, and that's also true for the 90 newton force. So in my equation here, for the sum of the torques that will cause the rod to rotate in counterclockwise manner, we have the torque due to the 190 newton force, all right? That's multiplied by its corresponding lever arm, which is 1.50 meters, all right? From the axis of rotation point B, the line of action of 190 newton is just half of the length of the rod, and that is 1.50 meters. While the lever arm corresponding to the 90 newton force is 0.50 meters. That is the distance of the line of action of the weight of the monkey from the right end of the rod, right? So, when you simplify, that will be equal to 330 meter Newton, all right? So this is the sum of the torques, all right, which we label here as CCWT. In other words, the torque that will cause the rod to rotate in counterclockwise direction. All right? So, this is just a reminder. When we write CWT or CCWT, all right, some would read this as the clockwise torque or the counterclockwise torque. All right? So we avoid saying that CWT is the torque or the clockwise torque and CCWT is the counterclockwise torque, because that would imply that we are describing the direction of the torque to be in a clockwise direction, and for CCWT, it is as if we are saying that the torque is directed in counterclockwise direction. The truth is, this only symbolizes the direction of the rotation of the body in question. All right? Again, CWT means the torque that causes the rod to rotate in clockwise direction, while CCWT is or means that the torque that causes the rod to rotate in counterclockwise direction. As a vector quantity, all right, the direction of the torque can be determined using the right-hand grip rule. All right, but describing and determining the direction of the torque, okay, we will discuss it probably in future episodes for this topic. All right, so equating the two torques, all right, that causes the body to rotate clockwise, and that is 1.50 meter times T1, and the total torque that causes the rod to rotate counterclockwise, when they're equated, all right, following the principle of torque, then we will have 330 meter Newton being equal to 1.50 meters T1. So now we are left with just one unknown variable, and to determine the magnitude of T1, we simply divide 330 meter Newton by 1.50 meters. So we will get the magnitude of the tension force T1 equal to 220 newtons. All right, this is the force exerted by the left root on the rod, whose direction, as earlier mentioned, okay, is 30 degrees with respect to the negative x-axis, or 150 degrees from the horizontal. All right. Now, one more thing. The unit for torque here is deliberately expressed in meter Newton. This is to distinguish torque from work. As we all know, the unit of work, all right, is Newton meter. So, to distinguish, or so that we will not be confused, okay, all right, we reverse the unit. Instead of Newton meter, we write it as meter Newton. All right, I hope that is clear. Meter Newton is the unit for torque, so that we can distinguish it from the unit of work. To compute T2, we first make use of our earlier concept. We said that the summation of fx must be equal to 0, right? So the x component of T2, or T sub 2x, is just equal to the x component of T1, or T sub 1x, but they are opposite in direction. So T sub 1x is just the product of cosine 30 degrees, which is 0.867, okay, when multiplied to the magnitude of T1, which we already computed earlier, all right, to 20 newtons, we will get 190 newtons as the x component of T1. So this is also the x component of T2. Then the y component of T1, which is equal to sine 30 degrees multiplied by T1, or 0.500 times 220 newtons, we get 110 newtons. And to get 2y, or t sub 2y, the y component of T2, based on our vector diagram here, all right, we make use of the fact that the sum of the vertical forces must be equal to the sum of the downward forces. That means to get t sub 2y, we just subtract the sum of 190 newtons and 90 newtons, which is 280 newtons, okay, minus the value of t sub 1y, which is 110 newtons. So we will get 170 newtons. And that brings us to our computation for t sub 2 using the Pythagorean formula. All right? So t sub 2 is just equal to the square root of the sum of the squares of t sub 2x and t sub 2y. That is square root of 190 newtons, square that, and 170 newtons square. So doing our math, we will get the value for t sub 2 equal to 255 newtons. And finally, we can proceed in determining the value of the angle theta based on equation number 1 earlier. All right, the working formula for finding the angle theta is just equal to the arc cosine, or the inverse cosine of the numbers inside the bracket. Means this is cosine of t sub 1 equal to 220 newtons divided by t sub 2. Right? T sub 2, which is equal to 255 newtons. So, doing our math or using your scientific calculator, we arrive at the value of angle theta equal to 42 degrees. So that's it. All right, we are done with our computation for the three target variables, T1, T2, and the angle theta. Till the next episode, mabuhay. Alhamdulillah, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.